Next is dichromate test or oxidation test. Okay. See, in this test, alcohols are treated with a strong oxidizing agent, acidified potassium dichromate, wherein even sodium dichromate is also used. So it's in general acidified dichromate, which is an orange colored solution. This, of course, is orange color. Okay. See, when sodium or potassium dichromate with a chromium in +6 state and orange in color reacts with sulfuric acid and forms sodium sulfate, chromic sulfate. Okay. Water and nascent oxygen. Let us balance this. 4, 4. Okay. These are nascent oxygen. Nascent means just born or just produced. See, chromium in +3 is green in color. This one. +6 is orange in color. +3 is green in color. So if this reaction happens, then the color of the solution turns into green. If not, remains the same. Let us see what happens with different alcohols. Coming to 1 degree alcohol. See, the primary alcohols with sodium dichromate and sulfuric acid, which of course gives the nascent oxygen required for oxidation. Primary alcohols on oxidation give aldehyde. Further oxidized to form acids, because this is a strong oxidizing agent. This mixture so once the aldehydes are formed, they are further oxidized to acid. During this, the orange solution becomes green. Okay. Now with 2-degree alcohol, we get ketone. Even here also, remove these two hydrogens along with oxygen. And even in this also, the orange solution becomes green, right? And now coming to 3-degree alcohol, special. In this case, there won't be any reaction. So therefore, the solution remains orange colored only. So this is a speciality. Tertiary alcohols have got no reaction with the sodium dichromate acidified. So primary and secondary alcohols turn the orange solution into green, whereas the 3-degree alcohols do not. Okay. Now it's oxidation. In general, oxidation, we can go for different oxidizing agents. I'll give you the list of all, but for now, remember, primary alcohol on oxidation. Now this nascent oxygen is from the oxidizing agent. Primary alcohols on oxidation give aldehyde. Aldehydes, with the same number of carbon atoms. This is important here. Now, if suppose a strong oxidizing agent is used, aldehydes are further oxidized to acids, again with the same number of carbon atoms. This is very important. Same with primary alcohol. Aldehydes with the same number of carbon atoms in the first step. In the second step, acids again with the same number of carbon atoms. Coming to 2-degree alcohol. Two-degree alcohols on oxidation give ketones, again with the same number of carbon atoms. Okay. See, on further oxidation, we get acid. But during this, a carbon atom is lost. Now, this acid will have one carbon atom less than the ketone. So this is same, less. In the first case, it is same, same. Here it is the same and less. Okay. So coming to 3-degree alcohol. On oxidation, 3-degree alcohols give ketone. But with one carbon atom less than alcohol. I mean the parent alcohol that we have started with. On further oxidation, we get acids again with one carbon atom less than the ketone. So here in this case it is less, less. So same, 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 less, and here it is less, less. Okay. Let me take malapride oxidation here. Related to what we have discussed. You know, it is in fact periodic acid oxidation. What is periodic acid? HiO4. Of course, we can use periodic acid or some periodate like sodium periodate or potassium periodate or lead acetate. Okay, so this is malapride oxidation. Used in case of three things, specifically for vicinal diode. I mean, when two hydroxyl groups are on adjacent carbon, alpha amino carbonyl compounds, that is course alpha hydroxy beta amine. Let me write alpha hydroxy amines is beta. Beta amino alcohol. Malapride oxidation is used in case of vicinal diols having two hydroxyl groups on adjacent carbons, alpha hydroxy carbonyl compounds. That means hydroxy and an aldehyde or hydroxy and a keto group on adjacent carbons. Then beta amino alcohol, OH and NH2 groups on adjacent carbons. Okay. Let us take them one by one. After the mechanism. Now, coming to the mechanism, consider a vicinal diol. Take periodate ion. The periodate combines with this vicinal diol, forms a kind of complex after the elimination of water. Look at it. Now the iodide, iodate. This one. This is the periodate. Still have oxygen of the vicinal diol. Only one oxygen is used. Now in this case, kind of rearrangements occur as and when this one goes here, this goes towards iodine, and then this one comes here. So this is how you get, this is C double bond O, another C double bond O, and the thing what we are left with is iodate ion. So this is periodate, and we ended up with iodate ion. One oxygen is given. Okay. Now let me give you some very interesting examples based on the oxidation information. This, of course, is very important when we go for biomolecules, the carbohydrates part. To know the structures of the carbohydrates. See, when this is treated with periodate, see what happens. As long as you got hydroxyl groups on adjacent carbons, this reaction occurs. You just cut it. This is going to give you, see, this part undergoes oxidation. A one-step oxidation specifically. Remember, one-step oxidation to form, see, because it is, I mean, as such, this particular carbon is a 2-degree carbon, right? I mean, after the bond is being broken, do not consider this portion now. Consider only up to this. Now, because that is a kind of secondary alcohol on oxidation give ketone. I'm telling you, do not consider this area, the portion below this. Okay, so that gives rise to a ketone. After one-step oxidation, this has undergone oxidation in just one step. Now, if you consider the middle one, it has OH group onto this side, even onto the other side. So this undergoes two-step oxidation. Okay. See, in the first step, you know, when you cut it here and here, this is simply a 1-degree alcohol. After cutting, it's a primary alcohol. The primary alcohol is now undergoing a two-step oxidation. What do you get? A primary alcohol in the first step on oxidation gives an aldehyde. In the second step, this aldehyde is further oxidized to acid. Hope you got my point. Two-step oxidation of a primary alcohol. Let me take the third area. Now, this, of course, undergoes oxidation just in one step, right? One-step oxidation. Only onto this side, you got a bond. I mean, you got a connectivity with carbons having OH. So just one-step oxidation, unlike the middle one, which had two hydroxyl groups onto its two sides. Now, see, after cutting it here, this is only a primary alcohol, isn't it? Be very careful. A primary alcohol in one-step oxidation gives an aldehyde. Is that okay? Check out the one-step and two-step oxidation. If you have hydroxyl group only onto one side, undergoes one-step oxidation. But remember to consider the carbon after the bond formation. Just like in this case, we considered it as a 2-degree one after the cleavage of the bond between the two carbons. Because anyway, on oxidation with pyridate, we are going to break this bond and we are going to rearrange it in forming the carbonyl group. You have seen the mechanism. I hope that is clear. Now coming to one more. A different one. We have taken vicinaldiol in the first case. Now consider alpha hydroxy carbonyl compound. a carbonyl group and a hydroxyl group on adjacent carbon. Of course, this is in fact a carbohydrate. Look at this. I told you that as long as you got the carbonyl group, I mean the aldehyde or ketone, in this case it is aldehyde. You got aldehyde and hydroxy. So undergoes cleavage. Even here also it is possible. Even here also it is possible. But here in this case it is not possible. You don't have any hydroxyl group. Is that okay? So as long as you got either two hydroxyl groups or hydroxy and carbonyl group, or even hydroxy and amino. Now let us just go on breaking the bonds. One step. Come on. Finally, here because we have broken two bonds, let us take two more. Two molecules. Let's see how many we are going to use in this case. The first one, of course, look at this. This undergoes a one-step oxidation. Right? Aldehyde in one-step oxidation, no doubt forms acid. Right? And here, of course, after breaking, we don't have anything, only the aldehyde thing. HC double bond O is what we have. So we get formic acid. Then look at, see, coming to this and this. See, these two are little special because they have got either the carbonyl group or the OH group onto both the sides. Look at this. When this also has got one more here, one more. Right. So that is why these two undergo oxidation in two steps. Look at this. Onto this side by this. Even this also. Onto this side. So let us just go for these two at a time, giving a two-step oxidation. See, after breaking the bonds, they are simple primary alcohols, right? Consider them as such. Do not see the carbons to which they are connected. Consider them as such. What I mean to say is, consider it this way. It's only a single carbon, a primary carbon. So in such a case, primary alcohols and oxidation give aldehydes in the first step, acids in the second. So in both these cases, we get formic acid. Of course, a total of 3 moles of formic acid. But I just wanted to give them in a separate note. Can we cleave the bond here? No, no, no. Because you don't have any hydroxyl group attached to this carbon. So this OH group undergoes cleavage only onto this side because it has a hydroxyl group onto this side. So only one step oxidation is possible for this. Because there is no hydroxyl group or no carbonyl group or no amino group onto the other side, we get, see, it is, of course, getting broken at this place, right? You are not breaking it here, but still it is attached to just one carbon. So is a primary one. It's a primary alcohol. Do not consider area above this. So what do we get? A primary alcohol obviously on one step oxidation gives an aldehyde, but because you got a methyl group here, you get this ethanol or acetaldehyde. Okay, so this is what is very interesting. We don't have any OH group attached to this, so no bond cleavage or no reaction. Okay. Take one more. Of course, the same thing, but with a keto. Okay. Now, let me just go for iodide. Come on, make it very fast. One step only onto one side. After the bond cleavage, it is a primary one. So just one step oxidation. What do we get? We get aldehyde. It's a primary. Now, see this group undergoes two-step oxidation, isn't it? So from this, see, keto in the first step oxidation forms an acid. In the second step oxidation, you get carbon dioxide, CO. Very important. First an acid, then CO. This is very important. Acids on further oxidation form carbon dioxide. Now coming to these three, check them out. All three undergo two-step oxidation. Hope that is clear. In two-step oxidation, see, after breaking the bonds, they are all primary kind of. Just imagine them as primary. So primary, when undergo two-step oxidation, in the first step they form aldehydes and in the second step they form acids. Come on. All three form formaldehyde in the first step, in the second step, formic acid. And finally, this. The last one, it undergoes just one step oxidation. Okay, it's a primary one after bond cleavage, right? Imagine it. Only one step oxidation of a primary alcohol forms an aldehyde. Let us take a beta amino alcohol. We have taken vicinal diols, alpha hydroxy carbonyl compounds. I mean alpha hydroxy aldehyde, alpha hydroxy ketone now. Now coming to beta amino alcohol. Look at this. Of course, it is an acid. But you know, with respect to this, your amino group is at beta. If suppose this is alpha, then this would be beta, right? Now, we can actually cleave the bond only at this position. This is okay. This, of course, is not okay because it's an acid. Even here also it is not okay because you have a methyl group, you don't have any hydroxyl, right? So let us just cut it only at one place. I mean here. So when treated, here we can write 1, 2, 1 here, 2 here, 3 here, 5, 5 more. Let's see how many here are used up. Now, from this area, what do we get? COOH remains the same.